So it will be in general, it will be quadratic. Sorry, which is the? It's n times n because that's a good point. I didn't tell you this, but this is pretty obvious because the recursion is so simple. It's in constant time per each step, but there are n times n many cases to work on. So it's also quadratic. Okay, usually in examples like this, the runtime is quadratic, but sometimes, as we will see in the next example, you can actually get by with n log n, but with a much trickier algorithm. So the next problem that, okay, I forgot to tell you, since we are at the longest common subsequence, how would you find the longest common subsequence for 3 sequences? Okay, so that's what is really tempting to think, but that's a good example. You have to be really, really careful. The devil is always in the details. So here is an example of 3 sequences when you cannot do that. So first sequence is A, B, C, D, E. The second sequence is A, C, D, E, B, D. So A, C, D, E, B, D, and the third one is A, B, D, C. If I find the longest common subsequence for the first two, what is it? It is ACDE. ACDE, right? It's of line 4. It's easy to see that you cannot do better than that. So the solution for these two is A, C, D, E. Okay, now when I take these two and this one, what is now the longest common subsequence? It is either AD or AC. But if you do it, is this a correct solution?
No.
It is not, right? Because the correct solution is actually ABD. ABD, ABD, and here you also have ABD. So it is not possible to do it in pairs. So first two and then the longest common of the solution with the third one. How would you then solve it by dynamic programming?
Would you just add in like a k and just do 3 arguments?
Exactly. So instead of doing it in a square, you would need a cube. So it would be 3-dimensional, right? And what would be the distinct cases that I would have to consider? And how many distinct cases do I have to consider? So if I have 3 of them, so what is the longest common subsequence of SI, S star J, and S bar K? This is equal to, if if AI is equal to BJ equal to CK, then this will be simply LSC of SI minus 1, S star J minus 1, and SK minus 1 bar concatenated with just AI. What else? What other cases do I have to consider? Do I have to consider A equal to B and or A equal to C, or do I not have to? Just think. So there is a mismatch. Not all three end up with the same. The only then way to make sure that you didn't miss anything is simply consider longest of LSC SI minus 1 as Sj star Sk bar then L longest, oops, I permuted this, longest common subsequent LCS of Si as J minus 1 star Sk and LCS of Si as star J as bar K minus 1, and there is no reason to consider whether two of them agree, simply because all what you know is that in order to be a longest common subsequence for all three of them, the endpoint must match in all three. If it doesn't, it makes no, you don't gain anything by considering whether Sj and Sk, for example, match. You simply try to peel off the first element of the last element of the first sequence, and you don't touch others. Then you peel the last element of the second sequence, and finally you peel off the last element of the third sequence. And you take the longest of these. Because all what you know is that the last elements, because they are not all three equal, simply at least one of them cannot be a member of the longest common subsequence. Okay, so this is one has to really be careful. You know, the devil is always in the detail. It's very tempting to say, okay, so I'll just do it first two and then the solution with the third one, but as you can see, it doesn't work. Okay, so what do we want to do next? We are going to do a whole bunch of problems, probably including at least part of the next week, because dynamic programming is absolutely, it is probably the most powerful technique that we are going to cover in this class. And in general, it's probably the most powerful design technique in algorithms altogether. So let's do again a problem that we did before for a special case, namely giving change. So let us now so assume that you are given denominations of coins. And this denomination includes 1 penny, so that you can give any amount of change, so that we don't have to worry about such details. So, you have values V1, which equals just 1 penny, and then V2, V3, up to Vn. So an increasing sequence. So V1 smaller than V2, smaller, and so forth, smaller than Vn. So these are your denominations. And you have certain amount of change C to give. And you want to do it, find a combination of coins worth C, which uses fewest possible number of coins. Okay. How would we do that? How would we find the solution for this problem? You see, this solution will be actually a little bit of cheating. Why would it be cheating? Because you cannot actually solve this problem in polynomial time, because we are going to do recursion on the amount to be returned. But this is an exponential time algorithm. Why is this so? If I take, say, C many steps, why is this an exponential of time algorithm? What does it mean that an algorithm runs in exponential time? Exponential time in what? When we say that an algorithm runs in time n squared, what do we mean by that? What is n? The n is the size, the length of the input, but the length of the input. So here, what is the size of this problem? So I have certain number. Assume that we fix this Vn, so this is all finite amount of bits needed to encode the values. But how many bits does encoding of C have? How do you write C? Do you write it in unary?
C the coin denomination?
No, C is the amount. So C is the amount that you want to return, the amount of change you want to give, given this, in fact, let's just say we have not, let's say we have 17 coins. So this all is just fixed 17 numbers. The only really parameter now, if we fix the denomination that can change, is C. But how many bits does it take to write C? Log C only. So, for example, if I tell you to give a change that is worth 1 billion, and optimal solution uses 1,000,000 steps, that's exponential in 7, right? Because this is 10 to the 7th. Is it? No, 10 to the 6th. Right? So notice, if my recursion takes 1,000,000 steps, 1,000,000 steps is exponential in 7 digits. Because it's 10 to the number of digits of C minus 1, right? So it runs, in fact, in exponential time. But that's the best what we can do. So for small amounts, it will be in fact, reasonably fast, but you should be aware this algorithm is in fact exponential in time if we do recursion by C. Okay, so let's forget about complexity at the moment and see when we do this, how would you recursively, if you know how to return optimally all values smaller than C, how would you find the optimal solution for C?
At the next coin.
Mm-hmm. So you would say something like this. Consider C, right? Optimal solution has to contain some coins. Remove one of the coins, any of them. So it will be, say, C minus V1. So I now have to give optimal, so the opt for C should be then opt of C minus V1 plus 1, right? Because if I take out one coin of value V1, what is left must be an optimal solution for the C minus V value, right? So it looks like this should work, but actually there is a problem with this. What's the problem with reasoning like this?
V1 exists.
Exactly. How do you know that V1 is used at all? But some coin it was used. So then opt of C will be min of opt C minus Vi over all possible I plus 1. Now that's, so what does this say? It says the following: to find optimal solution for the value C, I look for all possible values C minus Vi for any of the coins that we have. I find the optimal solution for the corresponding value and add 1. Why is this so? Because we don't know which values are involved in the optimal solution. So we have to test for all of them. Yes?
What does adding mean?
Because, okay, so I'm arguing like this. Consider optimal solution, right? Take any coin out. What is left must be an optimal solution for the value C minus whatever the value of the coin I took out. Because if it wasn't optimal, right, I could replace it with fewer number of coins and then put back the coin I took out and I would get a better solution. So from the optimal solution, if I take out any coin, the resulting the coins are optimal solution for S minus Vi, the value of the coin I took. But because I don't know in the optimal solution which coins are present, I have to give a try taking out all possible values for all denominations and find optimal solution for this value, and then just add the last coin that we took out, namely one with the VI value. Well, okay, so this is, you see, you are simply, it's brute force searching here in this step. It simply says, try to take out any possible, right? So this is this will give you the minimal number of coins Now, of course, if you also want to recover what coins are present in the optimal solution, when you find the mean, you have to incorporate in your recursive solution for which I it is achieved. So that you know what coin you took out, so that you can trace back the optimal solution. Okay, let's make now a short break and then we will continue with this kind of